Okay, so dear students, we are going to see this problem how to work out in the real Smith chart. So for this we have load impedance of 60 plus j 40 ohm, and at 30 meter long transmission line we have to calculate the characteristics input impedance, and the transmission line has the characteristics impedance of 50 ohm. So now how to do that? So first we are actually going to place the impedance. So first we have to write the ZL value. So the ZL value is nothing but 60 plus j 40, and we are going to divide this by Z0, so which is nothing but 50 ohm. So then we get the value of 1.2 plus j 0.8. So this 1.2 and 0.8 we have to map in the Smith chart. So how to do that? So for your understanding purpose, I have given the unit circle. So unit circle will pass through the center of the Smith chart. So that is what you have to look into now. Now in this we can see, first we have to see the real circle. So we can easily understand the real circle, which are nothing but the co-concentric circles, what you can see here, and just after 1 we have 1.2. so you can put a mark upon that, and this is the circle we have to follow. Next we have plus j 0.8. so this 0.8 we can easily see. When you see in the unit circle itself, you can see that the value is 0, 0.2, 0.4, 0.6, 0.8. so this is the 0.8 and this is the 1.2 line. So both are meeting at this particular point. So this meeting point only we are actually going to this is the value called ZL. Now this ZL value, once we have mapped, and that is the same point, we can also call that as the load reflection coefficient. Now keeping that as a reference, we can easily draw the we are going to draw the circle with respect to that. So keep it at the center, and this as a reference point, center as the reference point we are going to take, and we are going to simply draw the circle. So let us draw the circle. So sometimes it may be visible, and so it's better to keep the Smith chart light as much as possible. Okay. So this circle we call that as the VSWR circle. So this VSWR circle we have drawn. So next is we have to calculate the reflection coefficient. So this load reflection coefficient can be calculated with respect to the radius of the Smith chart. So we have to use the scale to calculate the radius of the Smith chart. So we can take this innermost we have to take the innermost circle, and keeping that as a reference point, and what is the value? So that is coming 8.5. so that is what it is noted down here, 8.5 centimeter. This may vary with respect to the size of the Smith chart. Always you have to calculate that. So in fact the very first thing you have to do is calculate the radius of the Smith chart and keep it as. So I have mentioned this is R naught. You can monitor, you can even note it as RS or whatever the value you can. Okay. So now we got the impedance point, and that is the normalized impedance point. That is the same point as the reflection coefficient. Now we have to measure the radius of the circle. So the radius of the circle, now it is coming approximately 3.4. so this reflection coefficient is 3.4 centimeter divided by 8.5 centimeter. So what is this value? This value is so it is 3.4 divided by 8.5. So this value is equal to 0.4. Okay, so here the value, and remember this value what I have calculated is the approximate one. With my eyes I have done that, but the accurate value is shown here in the PPT. So you just follow that. So you have to be very accurate as much as possible while you measure with the scale. Next we have to move the impedance point for a length of 30 meter. So this 30 meter, it is equal to 30 divided by 90 lambda times, so which is nothing but lambda by 3, and this is the electrical length, and we have to calculate the, sorry, this is the physical length, that is lambda by 3, and the next one we have to calculate is the electrical length, that is beta L. Beta is nothing but 2 pi by lambda, so lambda by 3. When you do that, you will get 2 pi by 3, which is equal to 120 degree. So for 120 degree we have to move that point. So for that first we have to find where is the present location of the reflection point is. So the reflection value, we can easily draw the line. So what my recommendation is, you just keep this point as a reference one and draw a line here. Always go up to the end outside the Smith chart. So now we are going to see this value. This is 50, 52, 52, 54, 56. So this is actually 56 degree. You can always note down here, nothing wrong in it. Now we have to add 120. So when you add 120, it will become 176. So we have to search for where is this 176, and here you can see this is 180, and this is actually yeah, here it is 170, this is 180, so 174. So 174 is here, and then now you can keep this point as the reference and you can draw a line, and you can always use sketch or something to do this workout. And now you can see that this particular point is meeting at this particular location, and that is nothing but our the input impedance, and which is also nothing but the reflection coefficient, input reflection coefficient point. So now how to calculate the value? So first, for this we have to use this. If you are going to use the real and imaginary part, so we can easily see here. So we have to extend this particular point, and this is meeting at this real circle. Okay, so this value is 0.3, 0.4, 0.5. So in between that a particular value is there. So we have subdivisions like 1, 2, 3, 4. So it is 8. So 0.48. So the reflection coefficient, input reflection coefficient, sorry, the input impedance normalized one, which is nothing but 0.48, and this is in the positive half cycle, so we are going to put J, and we have to find out the point. So for this particular point should be extended, so slowly we have to extend this particular point. So this is reaching this particular point now, so we are following this circle. So like that, so many circles will be there. So if this is the point, we have to follow this circle and we have to reach this particular point, and here also we have reached this particular point. And now we have to measure this value. So this is 0.0, this is 0.1, and this is subdivided into 10 times. So in this is 5, this is 6, so we are going to put it is 0.06. So sorry, this is actually before 0.5, so it is going to be 0.0. Maybe we can put 3 or 0.4 also we can put. Okay, so this is my observation, but the accurate value is 0.47 plus J 0.03. So that is the accurate value, and nothing wrong in it actually. Okay, so this is how we have to calculate the input. Now we have to calculate the reflection coefficient. So the input reflection coefficient, it is going to be the magnitude of that, which is already we know that this value is 0.4 and the angle is 176 degree. That's all. So that is what we have got.